Hello everyone, welcome to lecture 4 of week 7 of the course Power Network Analysis, in which we continue our discussion on the third last module, which is power flow analysis. In today's discussion, we'll exclusively talk about considering the effect of mutually coupled impedances and transformer taps, specifically off-nominal transformer taps in the bus admittance matrix. In the previous lecture, we have looked at the utility, application, and the assumptions involved in doing power flow analysis for a given power network. And the basis of power flow starts with basic understanding of bus admittance matrix, which in a way says or indicates that if there is a power network with n buses, the buses refer to points of common connection for sources and loads, and all these buses, they could be connected by several transmission lines, the transmission lines being modeled as long line model or short line model or medium line model depending on the line length and the operating voltage. And typically these lines, they are modeled in the nominal pi model with a series impedance, which indicates the line resistance and reactance, and half line charging susceptances indicating the line capacitance. So all these lines, they are connecting these n buses, and for this n bus network having few sets of transmission lines connecting these n buses, which are usually in a meshed pattern for transmission network, the associated bus admittance matrix, which we denote by the letter Y with subscript bus, is going to be a n cross n matrix, and which indicates essentially that Y bus for a n bus network is going to be a square matrix. In the previous lecture discussion, we have seen that if we consider only the transmission lines with their nominal pi models, then under such conditions, the Y bus also turns out to be a symmetric matrix, although we will see a specific case in today's discussion where the Y bus need not be symmetric. So in general, Y bus for power networks with off-nominal transformer taps are not symmetric matrices. And we also saw another crucial aspect while evaluating Y bus. In fact, the idea was or notion was that Z bus, which is also known as the bus impedance matrix, is nothing but, which also turns out to be a n cross n matrix for a n bus network, is nothing but the inverse of Y bus. And the inverse of Y bus, it is difficult to find this inverse in order to find Z bus if there is no proper connection between ground or neutral point through which the bus voltages are being measured. So in a way, the governing equations were that Y bus essentially correlates all bus currents in terms of Y bus with a function of all bus voltages. The bus voltages are all vectors here. So basically I and V, they are indicating n cross 1 vectors each, where each of the ith element or kth element of vector I and vector V could refer to the corresponding current and bus voltage at bus K. And if inverse exists, then associated voltages at all these buses can be represented as functions of bus currents, and this is possible only when Y bus inverse can exist. If this Y bus doesn't exist, then voltages or unique voltages could not be evaluated, even if the bus currents are known. Even if the bus currents are known, the bus voltages cannot be known for sure. So with that as a premise, I would also request the viewers to please go through the previous lecture to better understand how Y bus is evaluated for a given transmission line. We'll expand that discussion today for considering the effect of mutual coupled impedances and transformer taps. So if we understand or try to understand what is this mutual coupling and why this coupling at all exists. So I have taken a very simple example. The figure is taken from this particular source, wherein what is shown here is that there is a source which is sort of giving out alternating current, and this current is passing through a solenoid which is wound around a soft iron bar, and because of this alternating current which is changing time, which is changing its direction with respect to time, because there is a time varying current passing or flowing through this solenoid, uh, as per our right hand rule, which we have very commonly seen or made use of it in synchronous generator discussion as well as transmission line parameter evaluation. This time varying current is resulting in a time varying magnetic flux, the solenoid being a magnetic material and soft iron bar is a good magnetic material. So this is resulting in a time varying magnetic flux, and if this flux, which is dependent on the current variation, if this gets linked with a nearby solenoid, then this solenoid would also experience this time varying magnetic flux, as a result of which there would also be current induced or voltage induced. Basically voltage would be induced across this solenoid because of this time varying flux as per Faraday's law and Lenz's law. And if there is a path for the current to flow, provided there is a load connected across this coil, then this voltage which is induced would result in a flow of current, which would also be time varying in nature because the source which is generating it is also time varying in nature. And this basic premise we have also seen or discussed or understood it in the context of inductance evaluation, how nearby conductors can influence nearby magnetic induction. So basically this effect is exactly same as the electromagnetic induction as discussed in terms of transformers or transmission lines. Since mutual coupling can exist with respect to induction, which is electromagnetic induction, then it is expected that similar coupling can also exist because of electrostatic induction, which is what results in respective mutual capacitance and mutual inductance. That is the basis of why mutual coupling can happen. Mutual coupling often gets strengthened up for high voltages or high operating voltages, usually under low operating voltages. So typically for distribution lines, the coupling effect is little lesser, although in distribution lines, the lines are placed nearby, whereas in transmission lines with transmission towers having high right-of-ways, the higher operating voltage effect gets minimized or diminished because of large spacing. So corresponding coupling effect in transmission lines compared to distribution lines is more or less comparable or similar. So since the transmission lines or parameters can have mutual coupling effect thanks to nearby conductor or nearby capacitive effect, so it is important to consider the effect of these mutually coupled impedances in bus admittance matrix, because if the network itself is inducing or having such behavior, then it is important to model that or consider that model in the bus admittance matrix. So how do we go about that? What we consider is that we'll start with a very simple case. We have 4 buses marked as bus number M, N, P and Q, and between these buses Mn, pair of Mn and pair PQ, there exists a transmission, 2 unique transmission lines which could have their own impedances as ZA and ZB marked. For time being, we are neglecting the effect of half-line charging shunts, although on similar lines, half-line charging shunts mutual coupling effect can also be considered. So there are 2 impedances present between 2 pairs of buses Mn, Pq respectively, and these are mutually coupled with a value equal to Zm. And the dot polarity here refers to or indicates the direction of polarity in order of how these are coupled, whether the currents, if they are flowing into these dots. So basically the dot polarity means if these impedances carry currents in the same direction of dot, then the corresponding magnetic flux which would be created or resulting magnetic flux because of these inductive effects, they both would be additive. If the currents are flowing in reverse directions with respect to these dot polarities, then the additive effect is gone by, it is actually subtractive effect. So with this mutual coupling, let us see how this mutual coupled effect. So individually speaking, if ZA and ZB were to be only given, then essentially how would we have considered the corresponding bus admittance matrix evaluation? What we would have done, we would have taken the inverse of ZA, we would have found the corresponding admittance, we would have similarly found the admittance of ZB, and then the M comma M element of Y bus, which is referring to the diagonal element with respect to bus M, would have a component equal to YA itself. Similarly, YNN would also have a component equal to YA, whereas off diagonal elements MN or NM, they would be equal to minus YA. Similarly, YPP, which is a diagonal term of Y bus, would have an effect of YB. Same would be there for YQQ also. And the corresponding off diagonal term YPQ, YQP would be minus B. If these two lines were not mutually coupled, we would have the effect of considering these impedances or admittances as per the previous lecture discussion. The difficulty here is that these impedances don't exist in isolation. They are also mutually coupled by this Zm. So how do we consider the effect of Zm? So the idea is very simple. There is no complexity at all in this. What we do is we would always make use of the first principles and try to see whether the corresponding bus admittance matrix can be evaluated for this mutually coupled consideration. So for time being, we will ignore or we will not focus on this aspect. We will go by the first principles and try to see how things are. So let's talk about or see what is the corresponding governing equation behind the operation of this two transmission lines which are mutually coupled. I have assumed the current directions to be IA and IB for these different transmission lines. So if I write KVL from bus M to bus N, I would get VM minus IAZA, because I am moving along the direction of current. So I would have minus IAZA. And since IB is also flowing into the corresponding other coil, so because of this mutual coupling effect, the effect is going to be additive. So I am going to have a drop of IBZM, and eventually I arrive at bus N, so which is VN. VM, VN are voltage phasors of bus M and bus N in steady state with respect to some common reference. Similarly, if I apply KVL from bus P to bus Q, I would have VP minus IBZB minus IAZM equal to VQ. So if I represent this equation with a little bit of a rearrangement, this is what the equations would look like. As per the dot polarities, the inductive effects or voltage effects are additive, so corresponding voltage drops have the corresponding respective signs. Now if I have to find Y bus of this particular impedance element, always remember Y bus always links a vector of current with respect to a vector of voltages. What I have here is I have certain voltages as functions of currents, but I need other way around. I need my currents to be functions of voltages. So is that possible? So let's do that. If I can rewrite this equation in this form, probably I will be able to guess or estimate what would be my Y bus. So let's do that. So I have this as my basic equation, and as I told earlier, I need vector of currents, and these currents have to be bus injection currents. So in terms of injections, IM, IN, IP, IQ with respect to the corresponding line currents, IM and IN, they are reverse of each other in terms of IA, and similarly IP and IQ are reverse of IB with respect to each other. So I can write IM, IN, the bus currents, in terms of line currents IA, IB by making use of this 0, 1 matrix, which and I call that matrix or the transfer of that matrix to be a matrix. So essentially I am trying to replace the line currents IA, IB by corresponding bus currents, because I have to find Y bus between bus currents and bus voltages, not the line currents or the line voltage drops. So I have IA, IB vector in terms of this. Now this inverse exists only when ZA, ZB, Zm, Zm matrix is not a singular matrix. So basically the determinant of this matrix, which is ZA, ZB minus Zm square, it should not be 0. Usually when the lines or impedances are mutually coupled, in fact mutual coupling itself indicates that the maximum value of Zm that can exist between, ideally in terms of physics or in terms of the energy which can be stored, Zm cannot be more than the square root of product of Za Zb. That's the basic philosophy. For those of you who are interested of how this value is obtained, I would request my viewers to please look at the corresponding second year undergraduate mutually coupled admittance discussion, where you would find that in terms of energy which can be stored, the energy itself indicates this particular limitation. So in a way, if this is going to be true, then Zm square can never be more than Za Zb. Forget about Za Zb being equal to Zm square. So under the condition which is usually true, that the determinant need not be 0, this inverse can exist. And given this inverse, now I can find my line currents in terms of line voltage drops, but my Y bus needs to be in terms of not the line currents or voltage drops, but it needs to be in terms of bus currents and bus voltages. So if I know what is this Za Zmb matrix, I can evaluate its inverse and associate or find these small admittances. The expressions of these admittances can be obtained from one-to-one mapping with respect to these elements. And furthermore, the line voltage drops, again by use of A matrix, can be expressed in terms of bus voltages. So if I readjust things a bit, I have IA, IB in terms of this admittance 2 cross 2 matrix with multiplication of A, and here I now get the entire 4 cross 1 bus voltage phasor. And only thing which I need to do is to replace this IA-IB in terms of bus injection current, which is 4 cross 1 current. So basically I multiply this entire equation by A transpose, and effectively I get a resulting equation where 4 cross 1 bus currents are being expressed in terms of 4 cross 1 bus voltages, and the resulting intermediate equation which appears, or this matrix which appears, is effectively the Y bus matrix for these two mutually coupled admittances or impedances. So if I substitute the values of A transpose and A, where A matrix was this matrix earlier, and having known the small 2 cross 2 bus admittance matrix, if I evaluate them, then this is the 4 cross 4 matrix that essentially I would get. And this 4 cross 4 matrix has got few specific labelings. Now these labels are important to understand. Why is the labeling coming in? Recollect that when I said that Y bus is representing vectors of current in terms of vectors of voltages. So essentially, if I have to write ith bus current, let's say Ik, individually, not in terms of vector, if I have to write the kth element of I, which is Ik, and I have to find the expression of Ik in terms of Y bus and B, then essentially it would be summation of J is not J, let's say L is equal to 1 to capital N, assuming N buses, Y bus, comma, K, comma, L into VL. This is what the corresponding vector equation would result in for individual bus currents and bus voltages. So essentially, if I have to see the labeling or row, comma, column index of Y bus, recollect, you see that if Ik current exists, the first row index is referring to the current itself, whereas the column index is referring to the bus number or the voltage which is being considered. Similar logic or labeling is applicable over here also in terms of 4 cross 1 current and 4 cross 1 voltages. The first current is M, referring to bus current M. The first voltage is bus voltage M, and hence the first element of this 4 cross 4 matrix, which is YMN, should have a row, comma, column label of M, comma, M. The second element in this 4 cross 4 matrix refers to IM current with respect to Vn voltage. So that's why I have the second element as M, comma, N. And that's how the 4 cross 4 labeling can come into effect. Once I know this 4 cross 4 labeling, that which element is pertaining to which specific row comma column position. The only thing left here is to incorporate or superimpose this add-on matrix onto the actual Y bus. So how do we do that? We evaluate the Y bus as discussed in the previous lecture without considering the mutually coupled admittances or impedances at all. In fact, by without considering, I mean that we consider that those lines or impedances which are mutually coupled don't exist at all. Forget about the mutual coupling. We remove them from the power network and then evaluate the Y bus. For every such pair of mutually coupled admittances, figure out this 4 cross 4 matrix. Be very specific or clear about the row comma column labels, and then you have already evaluated Y bus in step 1 without the mutual coupling. For every mutual coupling, you are getting an add-on matrix which is 4 cross 4 matrix. The only part left is that each of these elements in this add-on matrix, which is shown over here, need to be properly superimposed or labeled on this Y bus which is without mutual coupling. So we superimpose these admittance matrices so that elements with identical row and column labels in add-on and Y bus, they get added together as per their respective signs. We'll also have an example towards the end of this discussion where this would become further more clear as to how the superimposition happens. Now, it may also happen that the mutual coupled impedances need not exist between two unique pairs of buses. That is, bus M can be same as bus P, bus Q could be same as bus N. So, there can be repeated labels sitting over here. It need not be actually a 4 cross 4 matrix. So, what is to be done in those cases? If one bus among these 4 buses acts as the reference or the ground bus, remember, for Y bus, there is no incorporation of reference or ground bus. So, corresponding row and column corresponding to the reference node is removed or deleted. It is not considered at all. And if there are 2 buses among M and PQ which are the same, so let's say if M is equal to Q with respect to the previous consideration that we had here. So, if M and Q are same, so instead of Q now here we have M, here also we have M, here also we have M, and here also we have M. So, if I have to find what are the elements pertaining to label M comma M, I would have 4 elements. Element number 1, element number 2, element number 3 and element number 4. Obviously, these elements are respectively multiplied by YMN, YMNPQ, etc., etc. So, essentially, I have this sort of arrangement where M comma M are 4 unique elements, and when I am doing superimposition, I can either reduce this 4 cross 4 into unique row and column labels. So, I can have a 3 cross 3 representation, because essentially here there are 3 unique labels and 3 unique labels here, or I should be very careful in mapping or superimposing 4 elements when I am considering M comma M in the add-on matrix. Similarly, if I were to look at how many M comma N elements exist, there are at least element number 1 sitting over here and also M comma N. Second element, there are at least 2 unique elements which are referring to M comma N, because N column label is having 2 row labels of M. So, I have to be very careful when I map M comma N element, I should consider 2 elements. So, that is how these elements, they are getting added up over here. So, let us say if this is M, this is N, this is P, YMU is getting added with minus YMN, that is how this term is coming in, and so on. So, process of superimposing, it essentially remains the same, there is no difference. Moving on to considering transformer taps on Y bus. Transformers, they aid in regulating voltages. As long as transformers have the role of adjusting voltage levels, then only their effect comes into picture. If there is a transformer whose transformer tap is exactly equal to 1, it is as good as considering that transformer and replacing it by a transmission line, because it is not regulating bus voltages at all. There can also be transformers which can regulate the phase angles between the primary and secondary voltages, and we call these transformers to be special phase shifting transformers. So, in essence, or in practicality, transformer step ratio need not always be a scalar number. Because it can also regulate phase shifters, transformer tap can also be a complex number. And by using this voltage regulation, as I mentioned yesterday in previous lecture, that real and reactive power flows, they are significantly affected through change of tap positions. So in case the tap is at nominal position, in per unit analysis, we have seen that the transformer impedance seen from primary or secondary remains the same. But usually the transformer tap is not at its nominal position, it has to be at off-nominal position. That's how the transformer role comes into picture. So we have a special mechanism of considering how the off-nominal tap position can be considered. As long as transformer tap is at nominal position, it behaves like a usual transmission line, where the transmission series impedance is same as the leakage overall impedance or reactance of the transformer. So for off-nominal position, we have this special mechanism where we have a transformer tap of ratio 1:A. A need not be a scalar number. It can also be a complex number depending on whether the transformer is regulating only voltages or whether it can also regulate phase shifters. And A, when it is equal to 1, we call the transformer tap to be at a nominal position. Usually A need not be equal to 1, and that's how it is called as off-nominal position. Again, in per unit essence, all these discussion is happening on per unit basis. So what we do, how do we consider this off-nominal position tap consideration in transformer in Y bus? We consider bus I and J between which this transformer is present, and this transformer has a series admittance YT, which is essentially inverse of primary and secondary impedances at nominal ratio in per unit basis. And having considered the leaky or the lossy component of the transformer separately, the ideal part of the tap is considered as it is, where the ratio A need not be equal to 1. So how do we go about considering this specific arrangement? So basically, if A was equal to 1, it would behave like that. Oh, Vx need not be considered, or in fact, this fictitious node X need not be considered. This line is directly connected to bus J, and hence Y bus can be easily evaluated. Since that is not there, the transformer tap present, so how do we consider its effect? So what we go again by here is, we go by the first principles. The first principle here is, we are assuming the injection current II into the network. We are assuming the injection current Ij into the network. And if I apply KVL between node I and node X, which is the fictitious node, then I get II is equal to Vi minus Vx into the admittance of the transformer. That is equation number 1. And since this tap position is an ideal transformer, so whatever is the power input to this transformer, same is the output of the transformer, because the lossy component has very well been incorporated into this admittance. So if I look at the power which is input to the transformer, the input power is basically complex power. So basically Vx into II conjugate should be equal to output power, which is minus Vj Ij conjugate. Why do I have a minus sign? Because I have chosen the injection current to be into the transformer tap. That is equation number 2. The transformer is an ideal transformer. The lossy component has been considered through this admittance. And the last equation is, if I have a tap 1:A between voltages Vx and Vj, then by voltage transformation ratio, Vx by Vj is equal to 1. I have equation number 3 here. If I have to find the corresponding Y bus for this transformer tap connection, I need a vector which should be actually vector I, which should actually be II, Ij. II, Ij are the injection currents into the buses between which transformer is present, as a function of some add-on matrix, and the voltages should be Vi and Vj. Vx should not appear at all anywhere. So if I can work out with these 3 equations and try to get an arrangement of this form, my purpose of evaluating Y bus is done. So let's see how it is done. So I have my first equation, as I mentioned, then power loss in an ideal transformer doesn't exist, so input power should be same as output power, and finally the voltage ratio. From there I can also find the corresponding current transformation. So if I rearrange these equations, so basically I have II here. I need to substitute Vx in terms of Vj, which I can do by using this equation. So I can get my first row of this Y bus matrix. And if I divide it by minus 1 by A conjugate, I can get my second equation. So if I do that, a simplification a little bit around, this is my add-on matrix, which is 2 cross 2 matrix, which is appearing in because of transformer tap. And A here is a complex number. It need not be a real number. It can be different from 1. It need not just be a scalar. So to incorporate the effect of transformer taps on Y bus, the first step remains the same, that is evaluate Y bus without considering the presence of transformer tap. For every transformer tap, evaluate the 2 cross 2 add-on matrix. This add-on matrix will have labels of I, J, I and J as discussed earlier, because the elements are relating to current I with voltage I, current I with voltage J, the second element. So if you be careful about these labels, the superimposition effect remains the same. Elements with similar row and column labels in add-on matrix and Y bus, they have to be just added. In case there are several mutually coupled admittances and transformer taps, individually evaluate their Y bus add-on matrices and superimpose them with identical row and column labels. The example here essentially sort of clarifies furthermore on that aspect. We have a 4-bus network where bus numbers are now labeled from 1, 2, 3 and 4. There are 2 transmission lines between 3 and 4, and between 1 and 3 we have transformer taps whose values, tap positions are given, and the corresponding series and reactances are also mentioned. We have to find the Y bus for this matrix, for this power network, 4 cross 4 network. So essentially at the outset, the Y bus should actually always be a 4 cross 4 matrix for this 4-bus network. So how do we do that? We convert or evaluate the line impedances into corresponding admittances first. We evaluate the admittance matrix. So since we have 2 elements between 3 and 4, so essentially we would have all elements as 0 in this Y bus matrix, except, so basically if I expand this a bit, this can be written as Y11, 12, 13, 14, goes on till 21, 22, 23, 24, 31, 41, 32, 42, 33, 34, 43 and 44. Since 2 impedances are present between buses 3 and 4, these elements would have an impact only on these 4 elements. Other elements, they would all be 0 in the Y bus matrix, and that is exactly what is shown over here. I have been able to mark the labels with respect to row. The columns also have a similar transposed labeling. 2 elements, 2 impedances, they have been now considered through these matrices. Now we have to find individual add-on matrix. So if we look at add-on matrix for a transformer between 1 and 3, we first convert this impedance into admittance. So this is my admittance here, and the tap is given as A equal to 1.25. The tap position is placed between 1 and 3. So I have my labels as 1, 3 here, and on top I have 1, 3. Similarly, if I put down those numbers, so I have this as my 2 cross 2 add-on matrix with this as the labels. Similarly, for 2, 4, this is my 2 cross 2 add-on matrix with corresponding row, column labels. And now I have only to superimpose these matrices with similar row, column labels. So if you look at the actual full matrix for 1, 1, I have only 1, 1 element sitting over here, whereas here it is 0, so I have minus J80. Whereas for 1, 3, 1, 3 in this matrix is 0, and here I have one element which is J64, which is J64 here. And likewise for 3, 3, I would have 3, 3, one element here, the other element is here, which when get added together gives minus 60.2 J as the final admittance. So with this, I conclude today's discussion, and the next lecture we will look at certain equations which define or create the premise of power flow. These equations are built on top of bus admittance matrix, and hopefully towards the end of next lecture we will understand few types of buses, their labelings and classifications in power flow analysis. Thank you.